Millennium Dome is one of the United Kingdom's most recognizable landmarks. It is located on the Greenwich Peninsula in southeast London, in England. It was intended to house the Millennium Experience exhibition, so it was designed and built between 1996 and 1999, with the architect being Richard Rogers and structural engineers Bureau Happold Consultancy. Millennium Dome is a mass-supported, dome-shaped cable network. It is consisted of the roof, mast, and the foundation. It is a circular structure with approximately 365 meters diameter, and its maximum height in the center of the dome is 52 meters. The roof is a cable network coating with a glass fiber fabric. The cables are responsible to support the self-weight of the roof and possible live loads such as snow, rain, and the wind. These cables are pre-tensioned just to make them stiffer. The loads are then transferred through connections to the 12th mast and consequently to the ground through the foundation. Because the masts are vulnerable to buckling, they construct the trusses and they are inclined slightly for vertical, with total length being around 100 meters for each one of them. Every mast lies up on 4 tubular lengths shaping a pyramid. Each length is founded to the ground with raking and vertical piles 10 meters long, used to reduce deflection and bending moments. There are also ground anchors for the cables in order to prevent the uplift movements of the cables.
Turning to the primary materials, steel was used in cables and masts, and also concrete in the foundation. They wanted a large open space for the exhibitions, and steel cables were the most appropriate ones, due to the fact that they are lightweight materials and can be used, offering the chance of long spans. By choosing a lightweight structure, the loads that are transferred to the ground are reduced, and as a result, less concrete is needed for the foundation. The secondary structural element is a coated glass fiber fabric, and it is chosen in order to provide a controlled environment for the exhibition. It is selected because it is a lightweight material. In this occasion, the entire roof weighs less than the air within the building, and because it fits with the concept of creating a lightweight structure.
Stability of the Millennium Dome. The stability of the masts should be firstly guaranteed, because they are designed to support radio cable lengths, so they have to resist compression and buckling. To ensure the stability of the masts, 12 cast insule piles are used. These piles were casted and hammered into the ground. Cables are also designed to ensure the stability. Radio cables are aimed to resist wind loads and uplift forces. They are attached to the roof and low points of the masts. Backstay cables were constructed and tied by ankle piles and ground anchors. Further series of piles were driven into the ground to support the building. The structure, the load-carrying behavior is largely dependent on deflections of the roof. When there is snow or heavy rain, pounding may happen, and the rain or melt water will continue to run into the pond, causing further deflections. This phenomenon may eventually cause local damage. Therefore, measures are taken to prevent the roof from pounding. The first method is to increase the slope of the roof, so water can flow down instead of staying on the roof. The second method is to increase the stiffness of these very long radial cables. When under load, these long cables may act as springs, but with pretension, they can be stiffer and the deflection can be reduced. The last method is to lift the circumferential cables out of the roof surface, because if they are on the surface, they can generate dams, which are possibly initial pounding, and they can prevent water from flowing down. Therefore, wishbones are used to raising the circumferential cables.
With cable structures, it's essential to consider the details about likely rotations of the cables at connections. If the radio cables were continuous through the node points, the flexing at those points would cause the cables to fail prematurely in fatigue. To avoid this flexing, the cables have to be terminated at each node and the connection details have to allow for rotation in both the vertical and horizontal planes. Barrel pins were used in clavies and plate-type fittings provide for these rotations. The masts are constructed from 8 323mm diameter steel tubes braced with rings at 2.5 meter spacing. The cables are connected with radio plates at the top and bottom, which are arranged to ensure that the cables theoretically meet at a single system point. The base of the mast is supported on the pyramid with a rubber port bearing to allow a small amount of rotation. One particularly difficult area was the need to work at considerable heights above ground level. With respect to the erection of the structure, masts, cable net, and fabric, the team addressed this to train experienced upsailers in assembly skills. This quite often turned out to be the better option and resulted in up to 100 trained sailors throughout the period of the dome erection, with the only substantial fixed temporary access platform provided for the erection of the central roof vents. The platform was formed by 50 meters high and 38,000 steel of steel frame, which itself earned an entry in the Guinness Book of Records as the largest independent scaffold in the world.
The Millennium Dome was the first major visitor attraction in the world not to have a cart park. It was serviced instead by a new Jubilee Line station, bus services, and river ferries. The water recycling treatment plant at the Millennium Dome is the largest of its kind in Europe and is a showcase for water treatment processes of the future. The water cycle from three sources: rainwater from the roof, greywater from 371 hand basins, and groundwater from a borehole on the site. This design is in the aim of providing 500 cubic meters per day to flush all the toilets and urinals through reed beds in the dome. Waste from toilets was then dried and burned to produce electricity, which was used to power the dome. So, how exactly does it work? First, greywater is collected in a balancing tank before biological treatment, which actually is a biological atterate filter. Groundwater is going through a hydrogen peroxide and held for a contact time to oxidize the hydrogen sulfide and ferrous, then pass through GAC absorbers to remove organic contaminants. The rainwater is passing through reed beds and a lagoon to be cleaned. Then water will go through a variety of ultrafiltrations and various osmosis membranes to flush toilets in the dome, which were equipped with a range of water-efficient appliances. By using water cycle, the dome is focusing on carbon reduction and sustainable way for environment. Let's look at a map of the location. The dome is located in this area and it surprisingly covers the most of the space, which provides a good example of land using.
The Millennium Dome was designed to host exhibitions, therefore an open space area was needed, so a cable network was the best solution to satisfy the key concept of functionality. The initial idea of creating something that looks like dome was accomplished by using cable network. In the beginning, the design wasn't successful because it didn't attract the expected number of visitors. However, after renovation and the creation of bars, restaurants, cinemas, shops, and arena upgraded the whole area. Nowadays, it is known as O2, and the final design was successful. Concerning the structural design, they could optimize the materials and elements of this structure in order to reduce the required cost, energy, and time.
It's fine, but not really what I expected.
Yeah, it's unique.
No, it's lovely.
Yes, I think it's a masterpiece.
Absolutely, it's memorable.